Dr. Atchison here, and we're still talking about Chapter 8, Attention and Awareness. This is our third video lecture where we're going to talk about why attention is selective, the benefits of that, and then the neural correlates of attention and awareness. So why is attention selective? What's the benefit of selective attention? It's evolved to deal with kind of the constraints on our system, our perceptual system, in a way that allows us to, based on how the brain represents objects. So selective attention evolved so that we can make sense of the world around us. One of the ways one of the reasons we think this is doing this is because of the binding problem. The binding problem is essentially how do we put back all this stuff into one object? So you have all these receptive fields, and some of them are looking at color, and some of them are looking at shape, and they're looking at orientation, and all of these different things. How does that end up as a thing in your brain? And our current idea is the solution to that is feature integration theory. Feature integration theory is, again, what we think why attention is selective, to fix this binding problem. A researcher named Anne Treisman proposed that there were two stages of perception, kind of a pre-attentive processing stage where our attention's not required, and that's where we're going to kind of have some of that more basic level bottom-up processing of color and orientation and those sorts of things. And then that second stage where attention is required. And the idea is that we solve the binding problem by selective attention. So by focusing on my computer, I can focus my attention there. I can focus my attention to those receptive fields, and I can ignore all the other objects that are in my visual array. And that we're able to kind of focus in on that, and that we're able to solve the binding problem that way. So there's no ambiguity in this situation anymore because I know I'm putting my conscious top-down processing on focusing in on my computer. And so I know that the shapes and the colors and those things that are related to this computer are related, the information that's coming in from my perceptual system bottom up is related to this top-down selective attention idea. And again, everything else is ignored. So any of that ambiguity in the rest of my visual field is being ignored by me not attending to it. Another reason we think attention evolved to be selective is this idea of competition for neural representation. So if an object matches the neuron's preferences, it will drive that neuron to produce a strong response. We've been talking about this since the beginning of the class. And objects with features that don't match will only produce a weak response. This is called competition for neural representation. Again, this idea that you're going to get a high response for one and a low response for one, but how do those things not cancel each other out? How are we able to kind of deal with this competition, that there'll be some strong responses and some weak responses? How do we not just get an average of kind of nothing in the middle? And again, the idea is the theory that we have, the solution that we have to this is bias competition theory. And what bias competition theory says is that the brain resolves this competition for neural representation by selective attention. That again, attention evolved to be selective to fix this competition for neural representation problem. By only looking at one object and only attending to one object, we are just representing the features of that object. Attention then biases that competition, so we're only focusing on the features that we're attended to, as if only that one object were present. These other things aren't essentially present. They're being ignored by our visual field, and so there's not competition from them as to neural firing or neural representation because we focused our perception on one entity. So kind of a quick review of attentional control. Attention is inherently selective. You can't physically attend to everything. You have to attend to things. And attention can be directed to different spatial locations and different features of different perceptual objects. It's very plastic in how you choose to use your attention and how you use this. And selective attention is the brain's mechanism for dealing with the binding problem and dealing with this competition for neural representation. The idea is that selective attention evolved to fix these issues in the neural system, to fix how we put everything back together, to fix how we deal with the fact that we do have a crowded optic array, and how do we only represent the objects that we're interested in. Selective attention is that fix. So to further talk about this, there is a launchpad activity that I want you to do that kind of looks at both top-down and bottom-up processing, and it looks at this through attentional capture and abrupt onsets. And there's a figure in your book, 811 on page 274 that also discusses this. But it looks at the issue of both top-down attentional control and bottom-up attentional control and how those play a role, again, in this selective attention and in our attention. So please do that Launchpad exercise. It is for class participation grade. So let's move on to the kinds of brain areas that are involved in attentional control. So most of these are on that what pathway, that dorsal pathway. And specifically, two areas that have been found that are really important to this are the frontal eye field, which is this kind of darker purple area that's in the frontal lobe, hence frontal, right? And the posterior parietal cortex, which is kind of the lighter purple that is in the parietal lobe. And we know this information from both studies with patients that have unilateral visual neglect, so they'll ignore parts of their visual field that they can physically maybe see, but they're not attending to. And so it gives us information, these kinds of lesions, these kinds of functional deficits, again, give us information about those functional modules. And then we also knew this from those single neuron recording measurements in monkeys. So with the monkeys, research has shown that, again, that posterior parietal cortex neurons are really correlated with what the monkey's attending to. So they did a study, and they had the monkey have 3 different tasks. They had a fixation task, a saccade task, and a peripheral attention task. And we'll go through all of those here in a second. So what they did is they trained monkeys to attend to different things and to pay attention to different things. In the fixation task, the monkey was supposed to pay attention to the fixation point in the black dot at all times. So you see these arrows, that's pointing to kind of where attention is currently, okay? So at all 4 times, attention was at that fixation point in the middle. The receptive field of the neuron that they were measuring is the orange oval. And then the visual stimulus they were trying to get kind of to see if it was going to cause this neuron to fire was the red line. Nothing's in the receptive field when the monkey is fixating at time 1. The red line appears when the monkey is still fixating at the center at line 2. So this is in the monkey's periphery. And you see we don't see an increase in neural firing. Attention is still at that point, but that point starts to dim color-wise. The monkey has maintained fixation there. That visual stimulus is still there, and we still have no difference in firing rate. And at time 4, the monkey makes a hand movement, and again, we have no difference in this. Okay, so this was all things that the monkey was trying to do. So attention never changed here. Attention stayed the exact same place, and we saw no difference in that neuron's firing rate. Okay, so this is part of the puzzle piece that's telling us that, these PPC neurons are involved with attention. So in the second task, the saccade task, starts out the same. The fixation point is there. The monkey was trained to attend to different things later. So we see the fixation point's there. Nothing's in the receptive field. The stimulus appears and the fixation point disappears, but the monkey's attention is still towards the middle. You can see those arrows are still towards the middle. And we don't see any difference between time 1 and time 2 in terms of firing rate. At time 3, the attention shifts to that stimulus, but the eye movements haven't happened yet, okay? So attention has shifted, but the eye movements haven't happened. And you can see that firing rate goes up. Okay, so this is before eye movements happen. Again, we talked about kind of that attention shift before eye movement. So the monkey is still foveating at the center, but the attention is now in the periphery, okay? And you can do that. You can stare at something, but look at kind of have your attention on something in the periphery, and that's what the monkey's doing at time 3. And again, what we're seeing here is that firing rate went up. Then the monkey physically moves his eyes and foveates at that visual stimulus, and the firing rate stays high. But the attention shift without the eye movement is what caused that increased firing rate. Again, this is evidence that the PPC is a critical part of the brain for attention. The third task was the peripheral attention task. Again, this one's going to be involving those hand movements again, similar to that first task. Again, time 1, time 2, attention's at fixation, and a focus is at fixation. And we see no difference in firing rate. Time 3, attention shifts again. Focus is still at the dot in the center, but we have a shift in attention. Again, the monkey's paying attention to the periphery, and that firing rate goes up again. At time 4, there's a hand movement, just as there was in the first one, based on what the monkey was trying to do. And again, that firing rate stays high. But we see that the firing rate changed when attention changed, before eye movement and the saccade task, and before hand movement and the peripheral attention task. So in both situations, attention is what caused this posterior parietal cortex neuron to fire. And again, this is really indicative of the importance of the posterior parietal cortex in attention. So again, the results show that the neuron's activity is not tied to the motor act, the eye movement or the hand movement, but to that attention, to the attention of that stimulus in that neuron's receptive field. That is what changed the firing rate, the monkey's shift in attention. And again, that's that important piece as to why the PPC is an important to attention. We also seen this with studying human activity using fMRIs. Studies with those showed that humans' PPC and their frontal eye field are both important sources of that attentional control, just like we saw with the monkey studies. It confirmed that the PPC is an important component of the brain's ability to control spatial attention, just like we saw with the monkey, that we were able to confirm that. Research was able to confirm that with fMRI studies using humans as well. And again, it provides really strong evidence that both of these brain areas are really important sources to control visual attention. Okay, so let's move on to the next section of the chapter, the last one that we're really primarily going to talk about, which is the neural correlates of consciousness. Now, this is an idea that there has to be some sort of correspondence between this neural activity and the conscious awareness. We just talked about this a little bit in terms of attention, but awareness, again, and attention can be kind of two sides of one coin. And so one of the ways that they're studying this, trying to find this correspondence between the neural activity and the conscious awareness, is through perceptual biastability. Perceptual biastability is that the picture doesn't change. The picture is the same, but we alternate between perceptual experiences. One of the ways we do this, one of the ways they test this is something called binocular rivalry. And this is where there's two different images and they're superimposed upon each other. And there's an image in your book that will let you look at this on figure 815 on page 279. And there's these two objects. Only one is going to each eye. In this case, we'll do this with our red-blue glasses that came with your textbook. And you're going to only have one image then go to one eye. And what's going to happen is it's going to oscillate back and forth between the two different images. Okay, so it's going to alternate between the perceptual experiences. So here's again that example. So this is in your textbook. I highly encourage you to do this because it's again, big psych nerd, but it's really interesting and fun. So put the glasses up and stare at the image for a while. For me, the house came up first, and the house gets really, really clear. And then somewhere along the line, it starts to become less clear and eventually switches to the man's face. And it goes back and forth. And I switched eyes to see kind of if it changed. So you can kind of play around with that for yourself. And what they saw is, again, this alternation between the perceptual experiences of looking at the house versus looking at the face. And this was also seen in those functional modules in the brain. So you can see here in the image B, there's a really high, when they were perceiving the house, we had higher firing rates for the house. And then we had lower firing rates for the face. And we see the blue line is going to indicate activity in the place area, and the red line is going to indicate activity in the face area. And again, we're seeing that there's more activity in the different areas depending on kind of the image that's being shown to them. So again, while they were viewing the face, the FFA activity went up, and when they were viewing the house, the PPA activity went up. And so again, we had this give and take between those based on the perceptual experience, flipping back and forth. So not only did the participants report that it flips back and forth, and again, you can look at this and do this yourself, it's very interesting, but fMRI confirmed this as well. And so then again, this is one way that they can study these neural correlates of consciousness. So again, when you're consciously attending to the face, you see that neural correlation to the activity in the FFA. When you're consciously attending to the house, you see that change in the activity in the PPA. And this is really supported by both bottom-up theories and top-down theories. So bottom-up theories are going to say that this is really happening because of neural fatigue. So again, you know, your brain's getting tired of seeing the house, and so it switches, it switches back and forth between these. There's perceptual switching is happening. This is based on that neural fatigue, just as we saw with the opponent color processing and things like that. This is just representative of that kind of overstimulation of that neuron. Whereas the top-down theories say that the viewer must know that this figure is 2, right? You look at that and you can say, okay, well, there's more than just going on. Even if you look at the glasses first and you haven't looked at it before. At first, you know, when I first look at it, I see them both, and then one gets clearer and the other one gets dimmer. But so you know this kind of going in, and so it switches between these, and it kind of knows top down that there are 2 possibilities, that their switch is possible. And research really supports both of these, both the primary visual areas as well as the areas such as the FFA and the PPA are really involved in these. So that this is not just higher order within those functional modules, but even for like on more basal levels in the neural functioning in areas V1 and such, that we'll see this both bottom up and top down pieces of the puzzle being involved. The final thing I wanted to talk about in terms of awareness and these neural correlates and consciousness is blindsight and vision. So blindsight is this phenomenon where somebody is cortically blind, okay? So we talked about, you know, blindness for different reasons. This is not something's wrong with the eye. This is something's wrong in the cortex. So this person can't see because of some sort of cortex damage. And what this phenomenon sees, this image kind of describes. They ask, the researcher would say, okay, you know, what's in this image? And the person's like, what line? Like, what's this line? I can't see a line. I'm blind. And so the researcher says, okay, well, just guess. What do you think it is? And chances are they guess right. I think this line's horizontal. So blindsight, again, entails this inability to report seeing, but have a good degree of accuracy as to different shapes, different locations, these different things. So again, this is telling us that vision and awareness are more than just kind of the sum of its parts. It can't just be each of these things. It really is all involved together, that attention and awareness are really important. And again, this phenomenon of blindsight really demonstrates this well. So that ends our conversation on Chapter 8 for attention and awareness. Thanks.